Hello, I'm Stefan Schneider from Paderborn University, and I'm going to present our paper on fully distributed service coordination. So this is joint work together with my colleagues from Paderborn University. And now I'd like to start with the scenario motivation of our work. So in network function virtualization, but also when we talk about microservices in a service mesh or even machine learning functions in a pipeline, we often have services that consist of multiple chain components. So for example, here C1, C2, C3, or C5, 4, 5, 6, and so on. These components could be firewalls, web servers, video optimizers, or machine learning functions that do some data processing, whatever. And in addition to these chain component services, we have our network consisting of distributed nodes, where each node has some kind of limited compute capacity. In addition to that, we have traffic arriving at the ingress nodes of the network. And here we assume that traffic is in the form of rapidly arriving user flow. So from the many different users that want to use our service. And yeah, and now in order to provide that service to these users, we need to scale it. We need to place instances of the different components at the nodes in the network. And we need to schedule all these rapidly incoming flows to the placed instances at runtime and also route them through the network. So for example, a placement could look like this, where we have multiple instances of C2, and of C1, and so on. And having these instances placed, we also need to schedule all these incoming flows rapidly at runtime. For example, some flows go down here, some up there, and so on. And the challenge here is, first of all, clearly to respect the node capacities, to respect the link capacities. And here we assume that our instances, they do not consume fixed resources, but instead they consume resources relative to the load that they're currently processing. So this depends on how we schedule this incoming traffic and how we balance the load. Yeah, so this problem of service coordination is not new. So there are existing approaches, but most of them, or all of them almost, are centralized. And that's a problem because such centralized coordination approaches require global up-to-date knowledge of the network. So complete knowledge, up-to-date of all the resource utilizations of all the incoming traffic. And that's not very realistic for large-scale networks. Of course, we can do some monitoring, but that A, requires a bit of overhead, and B, will not give us completely up-to-date information. For example, when we talk about Prometheus, the default monitoring interval is 1 minute. So you'll only have partial and delayed informations. But let's assume we do have perfect up-to-date global knowledge. Then we still have a second problem, which is that the decisions made in a centralized fashion also do not scale to large networks. So if we consider our scenario with user flows arriving rapidly all the time, then we may have thousands of decisions to make per millisecond on a network scale, and that just doesn't work. It doesn't scale, and that's a conceptual issue with centralized approaches. So not just for mixed integer linear programs, but also for heuristic approaches that are faster, but that still have this fundamental scalability issue. And I almost gave it away already. What we're proposing is fully distributed service coordination. So the exact opposite of these global centralized approaches. So in fully distributed service coordination, every node individually makes decisions locally and in parallel to the other nodes. So we do not just split the network into different parts and then again do centralized coordination of these different parts, but really each network does its own, each node does its own decisions, and this approach can be fully parallelized and there's no single point of failure. So basically for an incoming flow, a node has to decide whether to process that incoming flow locally or whether to send it to one of the neighbors. And the nice thing about that is that this can be done mostly based on locally available information. So about the resource requirements, about the available resources, or about the link utilization of the node itself and of the outgoing links, which is available and up to date locally, but not globally. And yeah, so the goal here is for us to maximize, first of all, the amount of successful flows. So to ensure that as many flows as possible are processed successfully and routed from ingress to egress. That's our primary objective. And then the secondary objective is minimizing the end-to-end delay from ingress through all the components to the egress node to optimize the service quality. Yeah, and the challenge here is, of course, to balance the load, to do all of these two things successfully, to avoid oversubscriptions, but also to keep short delay. Yeah, and for that, we propose two fully distributed approaches. First, greedy coordination with adaptive shortest paths, or short GCASP, and then a second approach that we call score-based coordination, also with adaptive shortest path, and we just abbreviate it with SBC. So let's have a look at these two algorithms and see how they work. First, GCASP, so the greedy coordination approach, where our design goals were to keep it simple, effective, fast, and frugal. And with frugal, we mean that the algorithm needs no global knowledge at all, except for the the network topology and the link delays in the topology, which we assume are both quite static and don't change over time, at least not so much. So we can assume that this is available globally. But other than that, it only needs local information about the node itself, about its outgoing links. And so we don't need any monitoring. We don't need any communication with neighbors. And overall, we don't have any communication overhead here. The main idea of the approach is to process flows greedily whenever that's possible. So locally at the node, if it has enough resources, and then otherwise forward it along the shortest path from the ingress to the egress node to keep the end-to-end delay short. Yeah, and if this is not possible because a path or a link on the path is congested, then we adjust the paths dynamically and reroute the flow in order to avoid drop flows. So let's have a look at the algorithm in a bit more detail. So the algorithm is executed by a node V once a flow F starts arriving. So for example, here, F starts arriving at the ingress node. And if V is the ingress node, like in this case, then it first has to compute the shortest path from itself, from the ingress node to the flow's egress node over here. This is done with Dijkstra, where we use the link delays as link weights, and then add that shortest path to the metadata, so similar to source routing. Then the greedy processing starts. So the node here processes F greedily, which means that if it has enough resources, then it starts the requested component of F if it's not running already, processes F, and once F is finished with that component, then it continues with the next component that's requested in the service, and so on until either the flow is fully processed, so it traversed all the components, or the node V does not have enough free resources to continue processing. And in both cases, the flow is forwarded now to the next neighbor along the shortest path, which is saved to the metadata. So we're forwarding to the next neighbor here, to V1. And on this way to the egress node, we continue this greedy processing. So also at V1 and at every intermediate node. And we repeat this until, for example, an outgoing link is congested. So this could happen. Maybe the link to the next neighbor on the shortest path is fully utilized and we cannot send the flow along there. And then in this case, we need to reroute. And again, we calculate the shortest path from the current node to the egress node, excluding the congested link from the topology. So then we get a new shortest path, add that to the metadata, and route the flow along there. Then finally, at some point, we reach the egress node, and if our flow F is fully processed, so it traversed all of the components in our service, then it can leave the network successfully. It's done. if this is not yet the case, so if our flow F is at the egress node, but it's still not completely processed, and the egress node does not have enough capacity, enough resources to finish processing the flow, then we still need to process the flow. We want to do this as close as possible to the egress node in order to keep the end-to-end delay short. And for that, we first select a random temporary destination node, in this case v3, and then send the flow towards that destination node. But again, on the way there, we do this greedy processing. So at some node on the way there, in this case, we call it v2, the flow will be done processing. So it traversed all the different components, and at that point, we no longer go towards this temporary destination, but immediately return the flow to its egress node, such that we can keep this end-to-end delay short. Yeah. So this is the GCASP algorithm. As you can see, it's quite simple. In fact, regarding complexity, we can pre-compute the shortest path that we need here at the ingress node. So we can do this up front and then just retrieve them in constant time. Also, most other operations can be done in constant time. So deciding whether to process a flow or not can be done in constant time. Where to forward can be done in constant time based on the pre-computed path. And only in the rare cases that an outgoing link is fully congested, sorry, then we need to reroute, and then we have a slightly higher complexity of O v squared, so of O of number of nodes squared. Yeah, so let's have a look at the second algorithm, which is SBC, score-based coordination, also with adaptive shortest path. And here our design goal was to leverage available information. So let's say in a practical network, as I mentioned at the beginning, we don't have perfect, up-to-date, complete global knowledge of everything, but very likely we have some knowledge, right? It's not just local knowledge. So maybe we do have some monitoring installed, and maybe it has some information, maybe not from the entire network, but just some neighboring nodes, but we often have some information. And the idea is to use this information and leverage it in this algorithm to, first of all, calculate node scores for all the different nodes that represent the scalability, the suitability of each node for processing a given flow. And yeah, this suitability and this node score calculation can be configured to whatever metrics are available and whatever metrics may be useful. And then we select the node with the highest score that's most suitable for processing. And by doing that, this SBC algorithm can actively choose promising nodes for processing rather than doing this greedy processing along the shortest path that we had in the previous algorithm. And to motivate this a bit, let's look again at an example. So again, here's our ingress node and our egress node. And what would happen for multiple flows that have the same ingress and egress node in the greedy GCASP is that they're both sent along the shortest path from ingress to egress, and they're competing for node and link resources on that path. And this can lead to either congested links and rerouting or a lack of node capacity. So overall to possibly drop flows or longer end-to-end delays. And so what we do instead in this SBC algorithm is that when a flow arrives, so first let's say F1, then we calculate these node scores from the different nodes in a network. And for example, now let's say V2 has the highest score, maybe based on how much resources are free because it has still free resources. And then we decide that this is our destination node. Flow F1 is sent there, and it's only processed there, not everywhere on the path. And then from there to the egress node. And then when the second flow arrives, F2, then again we do this calculation of the node score. And maybe at this time, V3 has the highest score because it has more resources available or because some other metric is better. And we send the flow over that way. And so by doing this, we can balance the load between these two nodes, and we can avoid this congestion and this these problems that we might have with the greedy approach. I'm skipping details of this algorithm for time reasons. If you're interested, ask me afterwards or have a look at the paper. For now, let's have a look at how these approaches work or how well they work in our evaluation. So for that, we looked at the real-world DFN network topology. So that's the German research network. The topology we looked at has 58 nodes and 87 links. We looked at scenarios with 3 services, with 3 components, and 2 components, and at stochastic flow arrival, so where flows arrive with random arrival time, randomized flow duration, randomized data rate, and we compare our 2 fully distributed approaches against a state-of-the-art centralized heuristic called BSP. It's from our previous work where we have the code available, and this centralized approach is called once for every new flow when it first arrives at the ingress node of the network. Then it calculates where to place instances, where to process the flow, how to route it, and all of this is then applied. For doing that, we assume that we have complete up-to-date global knowledge because that's required for such a centralized approach. And we also look at a variant called BSP Plus that we did for this evaluation that's tailored to this scenario with many stochastic flows. So it's an updated, improved version tailored for this scenario. So let's have a look at the overview of what we want to evaluate. One thing that we can already fill in is the required knowledge. So this is, of course, much better for our fully distributed approaches, which do not require up-to-date global knowledge. Instead, GCASP doesn't require any global knowledge except for the static topology, and SBC can use whatever information is available and leverage that. In addition to that, we now want to evaluate and look at the coordination quality of these different approaches in a variety of settings. We want to look at the stability, so how stable the coordination is over time, and then lastly at how scalable they are. So let's start with solution or coordination quality. And first, we're going to focus on successful flows, which is our primary objective, and evaluate how good they are there. So for that, we looked at the network with an increasing number of ingress nodes, so with increasing load. And we varied between scenarios with either homogeneous node capacity, so where all nodes have the same capacity, or heterogeneous node capacities or compute resources where some nodes have no capacity and others have a lot of capacities, and then yet others have medium capacity. So let's first look at the results here for the homogeneous node capacities. On the horizontal axis, you can see the amount of ingress nodes. So this indicates increasing load. On a vertical axis, the percent of successful flows. So watch out, it doesn't start at 0 here. So all of our approaches have quite high successful flows. All of our approaches have decreasing amount of successful flows with increasing load. So this is clear, more competition for resources. You can also see that this normal BSP doesn't work super well for this scenario with rapidly arriving flows, but the improved updated version BSP Plus does so. BSP Plus, as well as both of our fully distributed approaches, get close to 100% of successful flows. What's interesting here is, in this case of homogeneous node capacities, our greedy coordination approach is the best. It's better even than the other ones, and we think that this is because with the homogeneous node capacities, there are enough resources often there are enough resources on the shortest path from ingress to egress node. So this greedy processing along the shortest path works very well. In comparison, when we look at heterogeneous node capacities, the results are quite similar. So again, we have close to 100% successful flows with our fully distributed approaches and BSP Plus. But here, the greedy approach does not work as well. So it's slightly worse because it does not always find enough resources on the shortest path, and then it has to reroute or look for resources around the egress node. Yeah, next, let's look at the solution quality again, but at the secondary objective, so at the end-to-end delay. And again, for the first for the homogeneous node capacity case here, increasing amount of ingress nodes, so increasing load, and on the vertical axis, the average end-to-end delay, so from the ingress to the egress node. And for the fully distributed approaches in BSP Plus, this increases with increasing load. Of course, more flows have to be rerouted. And other than that, we can see that both of our fully distributed approaches are actually better than BSP Plus. And again, the greedy approach that sends everything along the shortest path has the shortest average end-to-end delays here, because this works really well for homogeneous node capacity cases. In the case of heterogeneous node capacities, it's again a bit different. Here, the greedy approach does not work that well, so it has to reroute more often and has higher end-to-end delays than, for example, BSP Plus, but it's still in the same order of magnitudes. And here, the SBC approach, the score-based approach, has the shortest end-to-end delay, and this is because it can leverage the available information about node capacities, for example, to directly send flows to wherever capacity is available and avoid nodes without capacity. So to summarize, when looking at coordination quality with homogeneous resources, the greedy approach is really great, and the other approaches are also good. With heterogeneous capacities, the greedy approach does not always work that well, but it's still quite good. So let's, stability, I skipped that plot for time reasons. It's in the paper and I can show it later on if you're interested. Basically, we looked at how our approaches perform over time. So not just after a fixed amount of 1,000 time steps like before, but during these 1,000 time steps. And we saw that all approaches do process and forward and schedule flows very stable. So it's not like the delay increases over time or the drop flows increase over time, but the coordination is very stable. So that's good. And now lastly, let's look at runtime and scalability. So the BSP and BSP Plus approach both make one centralized decision per flow, or when a flow has to be rerouted, whereas our fully distributed approaches make decisions at every intermediate node of wherever a flow arrives. So in total, they make a lot more coordination decisions than the centralized BSP approach. So this is a log scale. Also per flow, they make a lot more decisions. But the point is that these decisions can be distributed over all the different nodes in the network compared to the centralized approaches where everything is made at least at a single logically centralized node. So per node, our fully distributed approaches make a lot less decisions. And even more important, if we look at the runtime of our approaches, because they are so simple, these runtimes are even lower, even for the total case, compared to the centralized, more complex BSP and BSP Plus algorithms. And especially if you look at the runtime per node, they're a lot shorter or faster. And so overall, the scalability and the runtime of our approaches, of our fully distributed approaches, is just much better than for BSP Plus, which is a typical problem of such centralized approaches. So to conclude, I can say that fully distributed coordination works. We saw that GCASP and SBC both work, but have different strengths depending on how the node resources are distributed in the network. We saw that both of these fully distributed approaches achieve similar solution quality as a state-of-the-art centralized approach, but they don't need global up-to-date knowledge. They're much simpler and faster, and they can be parallelized massively. Plus, they're more robust to failures because they don't have a single point of failure. So overall, we believe that these fully distributed approaches can help improve service coordination and quality of service in practice. So thanks for your attention. If you're interested, again, our code is publicly available on GitHub. Feel free to check it out. Thank you.